Hello dear students! Today the topic of our lecture is procedure function-based spatial microstructures. The content of this lecture is following. First of all, we will recall heterogeneous object modeling, then to watch a difference between nature and artificial microstructures, consider problems with surfaces and voxels, then discuss the approach with using real functions for regular and non-regular procedural microstructures, and finally discuss the direct rendering of modeling in its fabrication. Let me remind you what a function representation is. This is a uniform representation of multidimensional point sets based on real continuous functions. The geometry in this approach is represented in an implicit form, but the representation of functions is broader than implicit surfaces or constructive solid geometry, because it has a broader set of operations and an extensible set of primitives. For modeling heterogeneous objects, the constructive hypervolume model was proposed by Professor Alexander Paсько with his colleagues. The model consists of the geometry described by function representation, and attributes described by function representation too. You can find more information in this article. Heterogeneous objects can be used for physical simulation, geological and medical modeling, and so on. Such objects have internal structure with non-uniform volumetric distribution of properties and complicated macrostructure. For example, heterogeneous objects can have such microstructures. By the way, can you suppose what is natural and what is artificial microstructures on this slide? The right answer you can see on this slide. So, task of modeling such examples of microstructures sometimes is not easy. A special approach is required for modeling and manipulation of such geometry. Modeling microstructures over surface or voxels has some problems. First of all, the size of models and processing time increase dramatically with the size of microstructures. Also, when manipulating a model with a microstructure represented by a boundary representation, unpredictable artifacts may appear in the geometry. An opposite method is procedural microstructures, when we define geometry of microstructures by continuous real functions and function representation. Constructive model is based on R functions, union and intersection. A sequence of mathematical expressions for modeling a regular infinite lattice is presented on this slide. First of all, periodic infinite slabs can be modeled by a periodic sine function. Then we get the rods at the intersection of the slabs. And finally, the grid is obtained in the form of a union of rods. As a variation of lattices, the variable thickness of the rod can be introduced, or a blending operation can be added to get smoothed rods. The lattice can be combined with a shell, and blending union operation can be also added between rods and with a shell. Here is an example of parameterization. Parameterization by distance can be introduced. Here you can see that lattice step decreases closer to the surface. Let's consider cellular microstructures. Such microstructures are constructed by replication of a unit cell. Advantages of function representation is possibility using space mapping for replication of a unit cell. The sawtooth wave can be used as a spatial mapping for replication of non-symmetric cells. The triangle wave can be used as a spatial mapping to replicate a symmetric cell. Here you can see an example of cellular microstructure, picture B, which was constructed by replication of a unit cell, picture A, union of 3 tori, with a periodic space mapping of a sawtooth or triangle wave. As example of multi-scale nested FRP structures, the 3 levels of nested tori balls you can see on this slide. The model was constructed using FRP plugin symbol for Rhino CAD system. During space mapping we can use spatial metamorphosis. In this example it is a metamorphosis from a ball to a union of 3 tori. The same method can be applied to cells within a grid and get spatial interpolation between 2 cell types. Here is an example of modeling a porous medium. It consists of the 3 steps. Perform basic pore replication, add distance dependency, and add noise. The GPU can be applied for acceleration, real-time ray tracing. Here you can see an example of direct rendering of a microstructure with a blending to the shell and between rods. Such microstructures can be fabricated using 3D printing. But today there is a problem with the intermediate format, which is based on the polygonal representation of the shape. Converting a complex microstructure to STL format leads to a huge size of the STL file and an increase in processing time. The second problem is that proprietary 3D printer management protocols do not allow to translate the functionally presented model into device management commands. The application of such procedural microstructures are listed on this slide. This is additive manufacturing and 3D printing, mechanical and bioengineering, geological exploration, medicine, digital art and entertainment, and Shiva project. Examples of applications in 3D printing are presented on this slide. Adaptive variable cellular and internal structures can be used for the process of topological optimization. Such microstructures based on direct finite element analysis and simulation can be linked to dynamic generative parameters, what affects the resulting shape of the part. Here you can see optimized model and fabricated part by 3D printing. Here you can see the workflow for modeling a lattice scaffold for a jaw bone. First of all, we take an initial jaw bone model, then the lattice is truncated by bone, and finally we add the shell by union of lattice with bone shell. Unicell replication can be used to design filters. Set theoretic difference between the surface and the volume microstructure can produce such complicated shapes shown on this slide. CAD systems based on the function representation have a good performance with microstructure modeling and rendering. Experiments with CAD systems showed that all CAD systems have failed with the array of 1000 Tory balls, but CAD system based on the function representation symbol for Rhino completed the task. Polygon-free and voxel-free approach has following advantages. Its interactive modeling, real-time rendering, fabrication, fitting and analysis. In future it will allow performing procedural multi-resolution modeling on micro and nano levels with infinite zoom.